The solution curve, integral curve. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already learned. In our previous lesson, we established a fundamental concept, that when we are solving a differential equation, we aren't just looking for a single numerical value, like x equals 5. Instead, we are searching for a function, which we can denote as y equals phi of x. Now, up until this point, we have mostly been working with these solutions using algebra, manipulating equations, and solving for variables. However, as we move forward, it is equally important to understand these solutions from a geometric perspective. In this subsection, we are going to bridge that gap. We will explore the relationship between the algebraic solution we find on paper and its visual representation, how that function actually looks when plotted on a coordinate system. This will help us transition from seeing just equations to seeing actual paths and shapes. Understanding the concept. Now that we've established in the previous slide that a solution to a differential equation isn't just a single number, but rather a function, let's look at what that actually looks like visually. When we perform the algebraic steps to solve a differential equation, we end up with a function, which we can denote as y equals phi of x. Now, if we take this function and plot it on a Cartesian plane, that is, our standard xy plane, the resulting graph isn't just a collection of points, but a continuous curve. This brings us to a very important formal definition. The geometric representation, or simply the graph of a function, y equals phi of x, that satisfies our given differential equation, is formally called the solution curve, or, alternatively, the integral curve. You might be wondering why we use the term integral curve. To understand this, just think back to the process we discussed in the first slide. Since solving these equations usually requires us to perform the process of integration, the curve we are plotting is essentially the visual result of integrating that original differential relationship. So, as we move into the next slide, keep in mind that this single curve is actually just one part of a much larger collection of possible curves. From general solution to a family of curves. When you find a general solution, you'll notice it typically includes an arbitrary constant, which we usually denote as c. Because this c can be any real number you can imagine, a single general solution doesn't just represent one single line on a graph. Instead, it represents an infinite set of different curves, all following the same underlying rule. In mathematics, we refer to this entire collection of possible graphs as a family of curves. To make this concrete, if we assign a specific fixed value to c, we move from the general idea to a particular solution. Each specific value of c gives us one unique, individual curve, which we call a particular integral curve. We will see a perfect example of this shifting family of curves in the next slide. Now that we understand that a solution to a differential equation is a function, let's look at what happens when we actually solve one. Step-by-step example. Now that we understand the theory behind families of curves, let's move from the abstract to the concrete. Let us consider a simple first-order differential equation to see exactly how a solution curve is formed. Take a look at our starting point, the differential equation di by dx equals 2x. To find the path this equation describes, we need to perform step 1, finding the general solution. To do this, we apply the process of integration that we discussed earlier. We will integrate both sides of the equation with respect to x. This gives us the integral of di by dx with respect to x, which equals the integral of 2x with respect to x when we compute that integral. We arrive at y equals x squared plus c in this context. Y equals x squared plus c is what we call our general solution. Keep this equation in mind, because in the next slide, we are going to see how that constant, c, transforms this single equation into an entire family of different parabolas. Step-by-step example continued. Now that we have successfully integrated the equation in the previous step to find our general solution, let's move on to step 2, where we identify the family of curves. Take a look at the equation we just derived. y equals x squared plus c, if you remember from your algebra classes, this isn't just one single parabola. It actually represents an entire family of parabolas. The reason for this is the constant, c depending on whatever real number we choose for c, the entire parabola shifts vertically up or down along the y-axis. This leads us directly into step 3, where we plot what we as particular integral curves. To make this concrete, let's assign some specific values to see how the graph changes. First, if we let c equal 0, our equation becomes y equals x squared, which is a standard parabola passing exactly through the origin. Next, let's say we choose c equals 2. Our equation becomes y equals x squared plus 2. Notice that this is the exact same shape as our first curve, but it has been shifted 2 units upward along the y-axis. On the other hand, if we pick a negative value, like c equals negative 3, we get y equals x squared minus 3. This shifts our parabola 3 units downward. It is crucial to remember that every single one of these individual graphs, whether it's the one at the origin, the one shifted up, or the one shifted down, is considered a valid solution curve. For our original differential equation, di dx equals 2x, as we will see in the next slide, you can think of these curves like different paths a leaf might take in a flowing river. Real-world analogy, the flow of a river. Imagine you are standing by a wide river where the water flows at different speeds and in slightly different directions at various points along the bank. If you were to drop a single leaf into that water, the path that the leaf follows is not random. It is strictly determined by the velocity of the water at every single point the leaf passes through. We can actually map this entire scenario directly onto the calculus we've been discussing. First, think of the differential equation as the map of the water's velocity. Just as the differential equation tells us the slope at any point, x, y, the map tells us the direction and speed of the water at every coordinate in the river. Second, the solution curve, or what we've also called the integral curve, is the actual physical path that the leaf travels as it is carried downstream. Finally, remember how we talked about the family of curves in the previous slide? Well, in our river, you could drop a leaf at many different starting points along the shore. Each of these different starting points, which we call initial conditions in mathematics, will result in a different, specific path. Each of these individual paths represents what we call a particular solution. So, just as one river can have many different paths for many different leaves, one differential equation can have an entire family of solution curves. Now, I know that looking at equations like parabolas and constants can feel a bit abstract. So let's step away from the algebra for a moment and look at a real-world analogy to help this concept click. Key takeaways. All right, let's bring everything we've discussed today together. We've moved from looking at differential equations as mere algebraic expressions to seeing them as geometric instructions. To wrap up, let's review our key takeaways. First, remember the term solution curve. When we find a function, such as y equals phi of x, that satisfies our differential equation, the graph of that function is what we call the solution curve. It is the visual manifestation of our algebraic answer. Next, you might hear the term integral curve used interchangeably with solution curve. This is simply another name for the same concept, and it's a helpful reminder that these curves are derived through the process of integration, just as we saw in our step-by-step example earlier. Third, we have the family of curves. As we explored with our parabola example, a general solution isn't just one single line. Because of that arbitrary constant, c, we actually have an infinite collection of curves. This entire set of possible graphs is what we call a family of curves. Finally, let's reflect on the deeper geometric meaning of what we are doing. A differential equation essentially acts as a set of directions. It defines the slope of a curve at any given point. X and y, the integral curve, is the actual path that follows those slope instructions perfectly. Now, before we finish, I want to point out a few common pitfalls to avoid in your upcoming practice problems, specifically regarding how to distinguish the equation from the curve itself. common mistakes. Now, before we wrap up today's lesson, I want to pause and highlight a few common pitfalls. As you begin working through more complex problems, it is very easy to fall into these three traps, so please pay close attention. First, be careful not to confuse the differential equation itself with the curve it represents. I often see students looking at an equation like di dx equals 2x and thinking that is the equation of the shape on the graph. Remember what we discussed in our earlier examples. The differential equation is actually a set of instructions describing the slope, or the rate of change, at any given point. The solution curve, such as y equals x squared plus c, is the actual result, the path that follows those instructions. Second, please do not ignore the arbitrary constant. See, it is a very common mistake for beginners to leave the c out of their final answer. If you forget the c, you are essentially looking at just one single, specific curve. But as we saw in our discussion about the family of curves, that constant is what allows us to represent an infinite collection of possible paths. Without the c, you lose the general part of your general solution. Finally, be wary of misinterpreting your graphs. It might be tempting to draw any line that looks like it fits the data, but a true solution curve, or integral curve, is not just any random line. It must be a specific function that, when you perform the process of differentiation on it, returns you exactly to your original differential equation. Every curve in your family must strictly obey the slope rules defined by the original equation. Keep these points in mind, and you will find much more success in mastering the geometry of differential equations.